All right, so now let's build a little bit on the last one. We talked about power. We're going to apply it to some of the stuff with light bulbs we saw just a little while ago. Take a look at the previous one. That as we increase the power, we noticed that the, just a moment, light bulb would actually get brighter. In fact, if we're not careful with it, it might get bright enough that it burns out the bulb. So this has a current of 180 milliamp. This has a current of 270 milliamp. And if I connect it right there, it'll probably burn out my light bulb. Now we have these additional ones because I would then connect it in line with this resistor. And we come on a little bit, we've got 130 milliamp here. And so we talked about the nature of the resistor being used to help control how much power goes to the light bulb. It's not quite very hot yet, but if I kept it going, it would build up more and more energy, more thermal energy, I should say, and it would get hotter and hotter. So one of the things that I want you to take into account is this, the scientific way that we measure the relative brightness of at least the old Edison light bulbs is they can be described in terms of their power, which brings us to old light bulb technology. So the ones that are hopefully going the way of the dinosaur, just because they're woefully inefficient and a bunch of other reasons to not necessarily like them. Please don't get too mad at me in the comment section, but I'm not a fan of the incandescent bulbs. This, for instance, is one that we got for holiday-themed lighting. So this was green. I've got a couple more red elsewhere. But this is marked as a 38-watt bulb is the power, and it's set for 120 volts. Now, one of the things that we talked about in class is when you plug things into the wall, a good estimate on the potential difference that it supplies is 120 volts. Now, it'll actually fluctuate because it uses AC instead of DC. And as a result, the actual amount of potential difference, the actual voltage, will fluctuate as a wave, effectively. That's how we drive them. Okay, I think one of these is the dead one, but that's fine. I'll figure it out later. Easy enough to test. One of the things that I wanted to follow up with is first we're going to talk about relative brightness of light bulbs. That's something that we're going to be looking at in class. We're going to treat light bulbs as ohmic resistors, even though they're not, at least from what we saw in the last one. You saw that the resistance changed depending on how much power I sent to it. If it's an ohmic resistor, then its resistance will kind of stay the same. Take a look at some of the videos that we've got for the lab on that to help supplement. In real life, these light bulbs, their resistances will change a little bit depending on when they heat up and cool down when you're using them. And so our actual numbers will be a little bit off, but we'll go ahead and check them. So this one says that it is a 38-watt light bulb. So we know that power is rated at 38 watts and that it is designed for a potential difference of 120 volts. So working pretty quickly, we can bring in one of the other equations that we had. Power equals delta V squared over R. We could solve for what the resistance of this bulb should be. So we said that 38 watts is equal to 120 volts, quantity squared, the whole thing squared, divided by our resistance. Great, I do a little bit of math here and I'm going to find that our resistance will be equal to 120 volts, quantity squared, divided by 38 watts. And you can go through and double check all of your units by breaking them down to what they're made out of, but I will say this, if you put SI in, you will get SI out. So we go through and we do this. I've got 120 volts squared divided by 38 watts, and I find that the resistance of this light bulb, when it is on and going at 120 volts in a standard socket, will have 379 ohms as its resistance. As a quick check, there's another way that you could do this. You could also say that power equals I delta V. And so we'd say that 38 watts is equal to our current times 120 volts. We could find that the current that this thing is intended for is 38 divided by 120. So this is intended to draw a current of 0.317 amp, 317 milliamp. And then we could then put that back in with V equals IR. So delta V equals IR, Ohm's law. We would get the following, 38 watts. That's my power. Delta V, let's see, so that is 120 volts is going to be equal to our current, which is 0.317 amps, times our resistance. We solve for our resistance, so I take 120 divided by 0.317, and I get that my resistance is equal to 379 ohm. We get the same outcome. Now, as a quick heads up, because people who are watching at a more advanced level, I know, and you know as well, this is usually connected to an AC outlet. That's the whole 120 volt RMS thing. For the purposes of our class, we only look at DC circuits, and so this is using an approximation that we're saying that this thing would be powered by a DC source. Now, there are some ways that you can actually get a pretty good adjustment of these power equations and use them to get a good estimate for what it would be in real life. And to underscore the differences between them, one of the settings on this is actually an ohm meter. It measures resistance. And so I'm going to measure the actual resistance of this bulb right now. It's coming up to about 30, though it's jumping around a little bit depending on how good I make electrical contact. But when I was checking this earlier, it came down to about 31 ohms. Now, why is that? That's noticeably different than the almost 400 ohms that we found. Couple things. One, as we talked about earlier, and you can take a look back at the other one the other video that comes right before this with power. I may actually put the two of them together because these are related. When I increase the power through this incandescent bulb, it actually changed the resistance of it. The resistance of this thing is definitely going to change when I actually connect it to power. Now, some of the things that cause that, and there's another video that talks about this, when the filament heats up, it's going to change its electrical properties, and as a result, its resistance will change. The other thing, as many of you on the advanced side are probably screaming at your video or at your screen right now, is that these equations have to be adjusted at least a little bit if we want them to connect to full AC, alternating current, which is the wall plug. For the purposes of this video, it's supposed to show how to work with DC values because that's what we start off looking at. So, please take into account that while we are solving this and we're getting useful values from it, in real life there are some additional alterations for it. For the purposes of what we'll be doing in lab, a lot of what we're doing will stay the same. Now, here's the other thing that I want to bring up. Now, that's a 38 watt bulb. We find that it should have a resistance of about 400 ohm. A brighter light, because this one isn't terribly bright, so if we went with a brighter light, say a 60 watt bulb, 60 watt. That's one that I like to put in some of my lamps. It's decently bright, but it's not overly bright. And so let's find the resistance we would need for that. Let's say that it also operates off of 120 volts. And that we're going to approximate this as a DC supply, even though technically it's not. But we could find the relative resistance of that light bulb would be, let's see, delta V squared over R. When we solve for R in this case, I would take 120 squared divided by, we said 60 watt, 240 ohm. What if I were to go with a really bright one, a 100 watt? Same thing, delta V is 120. The resistance for this one would be 120 squared divided by 100 watts. I would get 144 ohm. So one of the things that is kind of interesting is to get a brighter light bulb, we actually reduce the relative resistance. That actually allows more power to flow through it so that it can actually get brighter and brighter. So the actual construction for light bulbs can get a little bit more complex. Take a look at the video that I have marked for resistivity for more information. All right, so this is us applying some of this onto light bulbs, and an important thing to keep track of is one of the best ways that we can compare relative brightness is by looking at the power used by that bulb. Now, these equations that I'm showing you here, even though they're a little bit off from the real world values, that's mainly because of, well, AC, and that we're treating them as ohmic resistors instead of what they actually are, which is more likely non-ohmic resistors. But none of this directly applies to the other types of light bulbs, the ones that are compact fluorescent or LED. Now, I happen to like those, particularly the LED, because they are much, much more energy efficient. For a regular incandescent bulb, the amount of energy that they take and turn into light, only about 10% of it at most gets turned into visible light that you and I can see in. The rest of it is in the infrared. In short, these things have a lot of heat waste. They get very, very warm. Now, if you're using that, say, like in a doghouse or sometimes just in your own room, some people will use those as a cheap electric heater, which is fine as long as you're doing it safely. Make certain that there's no risk of fire. But most of the time, a lot of people are just using them for light, at which point we're wasting a lot of energy on heat. One of the last things that I want to talk about, speaking of wasting energy, there are some things that I wanted you to take a look at that we can work with. So, we can expand on this power thing. Let's go with, say, a 100-watt light bulb. Now, if you're anything like me, your parents may have gotten mad at you at one point or another for leaving some lights on, and they are totally not wrong. Don't leave lights on if you don't need to. But they would also bring up the, hey, it's costing an arm and a leg. So the question that I have is, how much does it actually cost? Okay, let's say that the light bulb uses 100 watts. That's what it's rated at, and it's a pretty bright light. We want to find out how much that would cost. Well, to do that, we need to introduce the idea of something called a kilowatt hour. KWH, kilowatt hour. Now, first and foremost, the old APB exam actually had a question about this, so I'll go ahead and bring it up, though I don't think the new AP1 likely will. Kilowatt hour is not a unit of power. In fact, kilo is just a modifier, so that means 1,000 watts. Watts is energy per time, and we're multiplying it. It's a kilowatt times an hour, which is a unit of time. You see that the time units cancel out. A kilowatt hour is actually a unit of energy. It's similar to a joule, or an electron volt, or an erg, or a BTU, a British thermal unit. All of these measure energy. Now, the main one that we use in class is actually the joule. Electron volts you may have seen in chemistry, or if you're doing some modern physics, and erg, well, if you're in astronomy, then you might see the erg. BTUs are the sorts of things that show up on a lot of imperial devices, so things that go off of the English system. All right, so first and foremost, kilowatt hour, even though it has the word watt in it because we're multiplying it by hour for time, it's actually a unit of energy. Now, here's the thing. You can actually go on, do a quick Google search, and you can find how much your local company charges for power. Right now, our rate is pretty much about 10 cents per 1 kilowatt hour, at least where we're at right now, and that's an average because they have kind of a sliding scale. I'm also rounding up slightly because it'll be easier to work with 10 cents. We could also say that as $0.10 per 1 kilowatt hour. So let's say that we leave this 100-watt bulb on for an hour. So here's what I'm going to do. I'm going to take the power, which is energy divided by time, and I'm going to multiply it by the time that I've left it on, 1 hour. Okay? The times effectively cancel out, and we end up with 100 watt hours. A watt times an hour. It looks silly, but it's a unit of energy. Power times time gives us energy. That's a watt hour. Now, if I convert this to kilowatt hours, well, 1 kilowatt hour is equal to 1,000 watt hours. That's the kilo. The watt hours cancel out. And we end up with 0.1 kilowatt hours. You leave a 100-watt light bulb on for 1 hour. Converting that over to kilowatts, or kilowatt hours, we have used 0.1 kilowatt hours, and we are charged 10 cents for every 1 kilowatt hour is $0.10. So I multiply those across, and I end up with $0.01. It costs you 1 penny to leave that 100-watt light bulb on for 1 hour. This is not an invitation to waste energy. We should all be working our best to conserve energy, but this is a great way that you can start actually estimating these. For many of you, you're going to be moving out on your own, and being able to predict how much it's going to cost you if you leave things on is going to be really useful. So let's take a look at a different one. So for instance, I have a computer. My computer has a power supply of probably around 500 watts. Now, I'm not using all 500 watts at all moments. It depends on how much I've actually got plugged in there. I'm actually estimating it some because I've actually got an 800-watt power supply in there, but I'm using a decent amount of that power, but not all of it. So let's call it 500 watts. Now, that's not including my monitors or anything else. This is just for powering up and keeping on the computer when it is on and active, not in sleep mode. Let's say that I leave that on for 8 hours a day. Okay, so I'm going to multiply those out, and I have 500 times 8. That's going to be 4,000 watt hours. Oops, I have a tendency of putting an R in on hour. I apologize. I feel it's supposed to be there, but when you get kilowatt hours, it's just kWh. All right, so that's 4,000. That's the same thing as I divide by 1,000. That gives me 4 kilowatt hours multiplied by 10 cents per kilowatt hour. And I end up with about 40 cents. That's how much it costs for me to leave that on for 8 hours. One of the things that I thought of while I was in grad school, and I ran some of the numbers and compared it to my electric bill and found out that it was the case, one of the things that I was bad about was I had a tendency of leaving my computer on just all the time. And sometimes I wouldn't even like it to fall asleep because it acted real sluggish afterwards. So a lot of times I would just leave it going. Wouldn't recommend that for a number of reasons. But let's say that I've got it going for 24 hours a day. Oops, not 2. 24 hours a day times 30 days. Now, the standard electric bill would run for a month. We'll call that about 30 days. Sometimes it's a little less, sometimes it's a little more, but this should give us a pretty good ballpark. Let's see. There are 24 hours per day, and I'm going to multiply that by days. I think I've gotten a little bit messy in my units here because I want it in kilowatt hours, but let's see. Yeah, let's do this the other way. So, real quick so that we can see the units work out fine. I'm going to leave this on for 30 days per 1 month, because I'm going to try and find how much this costs per month. Times 1 day is 24 hours. So the days cancel out, and I end up with the following, that I have 500 times 30 times 24. That gives me a whopping 360,000 watt hours per 1 month. All right, I divide that by 1,000 and I end up with 360 kilowatt hours per 1 month. Now you can ignore the per 1 month because basically I'm finding out what's happening on my electric bill. So 1 month is 1 electric bill. So 360 kilowatt hours times the going rate of about 10 cents a kilowatt hour. And this is going to be per 1 month. Kilowatt hour, multiply that across, and I end up spending $36 approximately per month on leaving my computer on the entire time. And that can really start to add up. In fact, if you go through and you check kind of the 100 watt light bulb, you're going to find that that's a couple of bucks if you were to leave that on all month. Hopefully, well, it would likely burn out, but neither here nor there. These things start to add up. You've got more than one light bulb in your house, and so it's money that you're just throwing away unless you actively need it. Here's an example of how we can get an estimate on what your electric bill would be. All right, so here's an application of